Hello, my name is Vladislav, and today I will present the machine BVI-03-74. You will see machine design, what it consists of, what equipment it is equipped with, and the principle of its operation. In front of you is this machine, which comes with an electrical cabinet, with control panel, measuring system, bed on which the first, second, third, and fourth supports are mounted. An additional middle support is available. Also included in the additional equipment are these pedestals on which it stands. They are fixed to the floor, poured with concrete, and the base of the machine is placed on top of them. Also included in the standard delivery set are adapters for balancing. In this case, they are presented one of each kind. In fact, two of each kind will be similar to you in the set. This adapter is designed for installation of large diameter flanges by centering with the help of this adapter ring, which will also be included in the kit. It will be as a sample. You will need to use this sample to make similar rings to the CARDANs you will be using. Then the next adapter is of cam type. It goes under the same flanges, only in a smaller size. Centering is also done by the same ring. And the last kind of adapter, it is a spline adapter for large trucks. For flanges like this. So it's installed in this way, and it's centered by these splines. And then it's in place. So the adapters are mounted on the machine with tapered fit. Also included in the kit are prisms, upper and lower prisms. You can swap them around if you need to. These prisms are for securing the center bearing by the stationary outer ring. It is also possible to install with a smaller type of prism, mounted on the backside of the machine, or with these bolts, and then you have the floating nuts. That is, in this case, how it is currently mounted. The support is also height adjustable. There's a screw on this side, and the support moves up or down. After that, it is fixed. The bracket is thrown in. The next support, similar. Also, these supports can be moved along the bed by unscrewing this thumb screw and the movements along the bed. The support is similar. Next is the guard. It also moves along the bed. When installing the shaft, the guard pin is moved at the back of the specially designated place for it. When the CARDAN starts to rotate, it is set in the work position before it starts. Then there is another spindle support to which the CARDAN is attached by means of adapters. It is also moved along the axle with this screw here, and there is a lock provided on this support. The CARDAN is mounted by centering this ring here to fit, bringing it in, connecting it, hit it with the support, then turn the CARDAN, lock the cams by the lugs. The cams should be parallel to each other. Tighten it up, that's it. The handle is fixed. The machine is switched on with this switch, from the off position to the on position. Then the signal lamp lights up that the voltage is supplied. A few seconds later, the green lamp lights up of the electric drive readiness. Then we move on to the remote control. Then the computer is turned on using the power button on the computer panel. When it starts up, the program will open automatically. On the control panel, you can see the automatic manual mode switch, the rotor acceleration and deceleration intensity switch, the indication of the locked or unlocked spindle, the indication that the rotor speed has reached the set speed, potentiometer, thanks to which we set the upper rotational speed limit, rotation start button, rotation stop button. In order to start working on the machine, it is necessary to set the CARDAN. Enter the calculation mode. Go to the setting mode. Then in the upper field, select the speed of rotation of the shaft in the transmission. In the specified range, set the shaft mass. Select the number of planes that are involved in this case. Now we have a 4-support CARDAN, and therefore all 4 planes are involved. If I had a 3-support or 2-support CARDAN installed, I would deactivate these planes. Then that's what we've set up. Click Continue. In the top column, we get the balancing tolerance in units of grams per millimeter for each plane. In this case, this is the first correction plane, the second, third, and fourth. The application radius are set in this column, so this is the place where we will set the testing, and after that, the balancing mass. The radii are the place on the pipe where we will be installing this. In this case, we're going to measure this diameter of the pipe on the side of the cross bearing to indicate its radius in the program. On the second plane, the radius will be this pipe diameter. On the third plane will be this pipe diameter. On the side of the cross again, and on the fourth plane, this one. In this case, the radii have been set correctly. Then we click on Mass Calculation. We get the permissible balancing in units of grams individually for each plane. We press the Accept button. We go to the next menu, where again we have each support is distributed by planes and common features are distributed by rows. The features common to them. So, in this case, we will have the permissible balancing for each support at the top. In the middle row, we have the calculated control mass, which is 5 unit permissible masses. That is, this allowable balancing is multiplied by 5, and this value is obtained. Similarly for each plane. And the last row is the test masses, which are available from 5 to 20 of the same unit permissible masses. So we multiply this same figure by 20, and we get something more. And everything that will be in this range, we can use as a test mass for tuning. After that, we take a weight that we have. That's in the range that we need. In this case, it will be 19.8 tenths of a gram, because we have a small initial imbalance on the drive shaft. And we're going to specify a mass for each plane. We're set. Press Confirm. We go to the Setup menu, where we will perform test runs. First, we make a test run without the set reference weights. Then, with the set weight on the first plane. After that, it is removed and moved to the second plane. The next test run is made, and so on. So we choose the start without test masses. Press Start Rotation. The CARDAN starts to rotate at minimum speed. Press Start Measurement. Then we increase the speed until it's displayed correctly. After the speed is displayed, we can see that in this case we have resonance on the first plane and on the fourth plane. Since the machine is over-resonant, we must go beyond that resonance and balance at speeds above the resonant frequency. So the recommended speed is, when balancing CARDAN shafts on the machine, BVI-03-74 is 1,200–1,400 revolutions per minute. And we, using this controller here, to set the rotational speed in the range we need. We're set. Then we wait for the stop button to activate. In this case, it is active. After that, we look at the stability of the display of angles and values for each of the planes. If the angle changes by more than ±5 degrees, I recommend turning on averaging. If it doesn't, then that's an acceptable measurement error, which can be neglected. The angles are stable. Press stop measurement, stop rotation. Select start with a test mass of 19.80 grams, plane 1 at 0 degrees. Here we see a display of the numerical value of the angle. We turn the CARDAN so that we have 0 here, or a value close to it. And vertically from the top, the tube plane of the first plane, we're going to mount our test mass. We will fix it with tape. We've secured it. Then we press start rotation. After the light bulb lights up, the speed is reached, we press start measurement. We waited for the stop button to activate. We checked the stability of the angles and values. Stop measurement. Stop the rotation. Selected start with test mass on the second plane. Remove the mass from the first plane. We tilt the tube again so that the monitor shows 0 on the monitor, and place the test mass on the second plane, again vertically from the top. Next, we press the rotation start button. Again, we wait for the speed indicator to light up, and we press the start measurement button. The stop has become active. Check the stability of the display of angles and values, recorded the measurement results with the stop, and stopped the rotation. Selected the start with the mass on the third plane. Dismounted the test mass from the second plane. Set the angular position to 0 degrees. Then on the third plane, vertically on top of our test mass, and fix it. Again, we press start rotation. After the display is shown, press start measurement. Stop the measurement cycle and set the rotation. Select start with mass on the fourth plane. Remove the test mass from the third plane. Weighing the angular position of the drive shaft to 0 degrees. And set the test mass on the fourth plane. Then press start rotation. Start measuring. Wait for the stop button to activate. And it's active. Control the stability of the angles and values. Press stop measurement button and stop rotation button. So all starts are made. After that, we press the result. Save the rotor under some name. In this case, it will be automatically saved under the name of rotor number 5. If it is necessary to replace it, we can click on the field and enter its name as we want. Click Save. We go to the balancing mode, where we'll see the first, second, third, fourth planes, the value of unbalance on these planes, the angle at which the unbalance is located, the allowable balance for each plane, and the correction radius for each plane. Also, each plane is highlighted in a specific color and displayed on the angle chart. So when I rotate the rotor, I'm going to have, in this case, set correction plane 1. And that's where I can put a balancing mass. But because it's so far out of tolerance, I won't do that. Let's go straight to the second support. Next, the necessary masses of balancing weights were prepared behind the scenes. Weights, tilting in this case plane number 2. We took a weight of 7 and 8 grams, placed it on the second plane vertically from the top, secured it with duct tape. The next weight will go to the third plane. Its mass is 10 grams. We tuck it so that the third plane is at the top. Install this weight on the third plane. Fix it. After that, we take the weight for the fourth plane with mass 13 and 3 grams. Angle it so that the fourth plane is vertically on top. Set the balancing weight and lock it in place. Press the start rotation button. Wait for the stop button to become active. Stop button became active. Look for the stability of the display of angles. In this case, the machine was in automatic mode, so it stopped measuring and rotation automatically. In manual mode, I would have had to press the stop button manually. The results of the balancing are that each of the planes is deep in tolerance. Once we've achieved these values, we need to weld these weights on and do another run to make sure that the values have not changed in any way and are not out of tolerance. Once that's done, click on the report button, Create. Enter the name of the operator, select the first run as the start run and the last run as the end run. Click the Create button. The report is created automatically. The protocol is automatically created. The name of the rotor is specified. The speed at which the balancing was performed is specified. The number of planes is specified. The tolerance for balancing is present. According to the results of balancing, the rotor is OK. And then we see the name of the operator, the date synchronized with the computer. And when we print it out, we can either sign the report, then we can either save it or print it out. Also by functions here, there is diagnostics of a condition of sensors. Accounting of the unbalance of the equipment, it is necessary to do it on this type of adapters. Why? Because the spline centering accuracy is about of 2/10 millimeters. And there's also a harmonic analysis function, which can be used to determine whether it makes sense to balance the drive shaft, whether there are any mechanical faults in the drive shaft, or whether there aren't. There are none. In the process of rotation, we will observe how these columns change. This is again the first plane, the second, the third, and the fourth. The first column will be for unbalance. That's what the machine can eliminate. But if any of the subsequent columns, if they're larger than the first column, then it will make it difficult to measure the system, and will also indicate that there is a mechanical fault. In a particular case, the second column will be responsible for a cross bearing that is broken in one of the positions, which is either this one or this one. For example, either this is how it can be broken, or this is how it can be broken. The fourth column is when there will be a cross bearing broken in both the vertical and horizontal positions at the same time. The third and fifth column will be responsible for the spline, and everything above the fifth column, beyond the fifth column, will be responsible for the center bearing. So if we see any column higher than the first column, then it's going to be necessary to repair and replace the unit. In some cases, it is necessary to take into account the eccentricity of the tooling for proper balancing. For example, when balancing shafts with end splines. The machine has a special function in the menu to compensate for tooling eccentricity. The machine is mounted on cubes. Their height must be adjusted to the height of the worker. Ideally so that the drive shaft is at the level of the navel. It can also be slightly higher and put a wooden plank under the machine at the place of work. So it is installed either on concrete cubes or you can buy steel cubes together with the machine. These will also need to be poured in concrete and attached to the floor. They're mounted on 4 anchor bolts. The holes are provided in them, and then to them with the help of a special clamping bar using 2 M16 nuts will be attached the machine bed. You can see it here. Here you can see the clamping bar and 2 M16 nuts. Connectors are provided for connecting the machine, and there is also a space for inserting the base of the supply cable. The connectors are labeled, located on the right side of the electrical cabinet. Also, they have different number of legs, i.e., it is impossible to mix them up. Also on this side is the grounding bolt, which will also need to be connected. The wiring diagram is located on the door. The electrical panel is located here. At the very bottom of the electrical panel is the power inlet. Next, the vibration sensors will be connected from the back of the cabinet to the measuring device. These are the first plane, second plane, third plane, and fourth plane vibration sensors. This is the automation cord, the COM port cord, and the angle sensor. Once the connectors are connected, the metal sleeves need to be secured with this clamping bar.